So, hello. Is this volume okay? Okay, great. So let's start. Today we are going to talk about decisions, and this is relevant to the information theory, but it's more applied. And there are a lot of scenarios in, for example, building up natural language processing systems or making scientific discoveries that requires the knowledge that will be described in this class. So let's first take a kind of side walk and think about a question that we usually do not think about. Does the sun rise from the east? Yeah.
Can you use some?
So the volume is still not large enough? Okay. How about now? Is the volume okay now?
Yeah.
Okay. It's better. Yeah, I need to adjust the location. Sorry. Yeah, whenever you find the volume is like too small or too large, just raise your hand. Yeah. Question?
Still your speaking is not getting registered in the mic.
Like, did you prefer like the volume is?
Even if you relocate at the mic, your sound is not coming from the mic; it is coming from the.
The sound is not. Oh, because I'm using the remote. The wireless one today, and hopefully the wireless one will be more flexible. So there's no sound coming from the podium, and I'm using the wireless one, and there should be sound coming from the.
I understand, but still like the mic that you have holding on your cloth, that is your voice is not registered in there.
I think what he's asking is if we can pin this on higher.
The higher, okay.
We can pin it a bit higher so that your voice is more.
Okay. How about I just talk louder? This should be okay. Yeah.
No, speak.
Hello.
What's that?
Okay.
Yeah. You have to speak it a little louder because this is on the lower side of.
Yeah. Sure. I'll just talk louder.
This is also on.
Oh no, this is mute. So I'm just using the wireless microphone.
Yeah, you can on this also.
Oh, so we use both.
Yeah.
Okay.
And speak loud.
Yeah, sure. So we all know that the sun rises from the east, and where does so this is a sort of knowledge that is that we take as granted, and we do. So we are going to feel very surprised if one day we see the sun rises from the west. And how does this knowledge come from? So it comes from repeated observations. So every day, since we can remember things, we remember that the sun rises from the east. And the repeated observations confirm this belief, and this becomes justified belief, and our belief about this statement becomes reinforced and solidified. So there is a similar pattern in other types of discoveries. So the knowledge comes from repeated observations of the event. And there is a workflow here. We first make a hypothesis, and then our observations confirm the opposite of the hypothesis. So this workflow is extremely common when discovering some new knowledge. And in this lecture, we are going to describe a standardized procedure of making this type of discovery, which is hypothesis testing. So usually the procedure is that we first state a hypothesis, and this will include stating both sides of the hypothesis. We state the null hypothesis and the alternative hypothesis. And step 2 is to compute some test statistics based on our observations. And step 3 is to compare this statistic to a critical value and report the test result. Usually, we compare a p-value to a significance level, which is usually taken as alpha equals 0.05. If the p-value is smaller than this critical significance level, then we reject the null hypothesis and state that there is the alternative. We tend to believe that the alternative hypothesis is true given the observation. Otherwise, we do not reject the null hypothesis. So, what do we mean by null hypothesis and the alternative hypothesis? The null hypothesis states that nothing has changed. There's no new knowledge out there. Nothing is new. Everything just goes the same as before. And the alternative side is the alternative hypothesis, which we usually write as H1. It usually states that there are some new meaningful findings. So the actual contents of the null hypothesis and the alternative hypothesis should depend on the actual problem setting. And in the remaining of this lecture, I will describe the t-test. T-test is the most common statistic test in natural language processing, and actually machine learning as well. There are some other types of tests. What's this sound? Okay. There are some other types of testing as well, but I'll describe later. And for now, let's just consider the t-test to be the test that you're going to use in the natural language processing. Some of the problems that can be studied by the t-test will include questions of this kind. Does someone named Elon send tweets of 100 words long? Or I add a layer to a neural network, or I made some adjustments to the hyperparameters in a machine learning system. Does the prediction accuracy, does the new system make better predictions than the previous systems? Or a group of participants try to take a new recipe for a month. Do their weights change by this new recipe? So with some observations and the statistics that are collected during these observations, you can apply some t-test and quantitatively answer these questions. So the answer towards this question would be in the form like the p-value is, for example, 0.03, which is smaller than 0.05. So we conclude that Elon sends tweet of around 100 words long. So actually, the actual report would be something like the mean length of his tweets would be 100. Or the opposite, the mean of his tweet length would be different from 100. Before going to the how to compute the statistics, there are some concepts that I want to clarify. We need to tell apart between the sample versus the population. A sample is the event, and the population is the random variable. So sample is known, and the population is not. But we are trying to make some hypotheses and try to make some scientific discovery about the population based on our observations of the samples. So in the sample, we can get, for example, 100, 200 tweets, or even 1,000 tweets, or even all of the tweets available on the internet. But this is still different from the population. The population is unknown. It is the random variable. In the problem of deciding the average length of this person, the population includes both the past tweets and the future tweets. So it's really unknown, and we can't really directly measure the population, and we can only directly measure the samples. And recall what we see in the last Wednesday. Darth Vader is saying something versus what Darth Vader says. So the Darth Vader saying something is a random variable, but what Darth Vader says is the sample, is the event, and it's the observation. So let's look at the one sample t-test. One sample t-test is usually the first type of t-test that was introduced in the statistics class, and you've probably already seen that in stats 230 something. The null hypothesis is that there's no new finding, which is the average length of the tweet is 100, and the alternative hypothesis is that the population mean is different from 100. So the procedure of computing this t-test is that we compare the mean of the samples, so with the hypothetical population mean. So the hypothetical population mean is set to 100. It's stated in the problem. And we just use a symbol, mu, to represent the hypothetical population mean. And for the sample mean, we collect a sample of n tweets. And here n equals 50. And we compute the average length of this sample tweet. And then we plug into this function from SciPy stats. So for the purpose of CRC 401, we do not go into the details for example, taking the mean and computing the t-values and p-values, because that would be, if you're interested in the details in computing the p-values and t-values, you can take, for example, a grad course in stats. And this function is going to give you the t-value and p-value. So there are some notes that I want to emphasize. So first of all, the true population mean is unknown. So although we hypothesize that the population mean is 100, the true population mean is unknown. Okay? And the second note is that we need to assume that the population is normally distributed. So this is required by the t-test. The reason why this is called a t-test is that the mean of the samples from a normally distributed population follows the t-distribution. And this is why this procedure is called a t-test. And question?
Is there a reason that we are making the alternate hypothesis as population mean is different from 100?
This is just following some conventions. Yeah. It follows the convention, and everyone else is following the same convention. So there's no very specific reason behind using this as the null hypothesis and using that as the alternative hypothesis. So there's a heuristic that the alternative hypothesis is usually that we find something new and we see something surprised, and the null hypothesis is that there's nothing new. And yeah. But for the actual null hypothesis and the alternative hypothesis, it's really kind of arbitrary. We just follow the conventions, and like everyone does. So in order to check whether this population is normally distributed, you can use another statistical test, which is called Shapiro-Wilks test. So Shapiro-Wilks test also computes some p-values based on your samples. And you plug in the samples, and this test returns a p-value. And based on this p-value, you can infer that whether this population is normally distributed or not. So if this population does not follow the normal distribution, you should use the Mann-Whitney U test instead of the t-test. And a question?
So sorry, what does the t-variable do?
T-variable is the so
in the return value of this test. So P is like p-value, and then there is T, which is the first return. What is it?
So both t-values and p-values are the results of this test. And actually, the p-value is the probability that the t statistic gets bigger than the threshold. And in order to facilitate fair comparison across different statistical tests, you can take a p-value, because almost all the statistical tests will report a test statistic plus a p-value. So you can take the p-value and compare it to across different statistical tests. But for the t-test, the test result is the t-value. So you can consider that in this way. In a final exam or a midterm, you will see a raw score and a percentage score, and p-value is like the percentage score, and the t-value is the raw score. So you get multiple tests you can get multiple test scores in one examination, but these two scores kind of describe the result of the same test. Okay. And actually, the coding examples for Shapiro-Wilks test and Matt-Whitney-U test is described in a Jupyter notebook. I already uploaded the PDF of the Jupyter notebook to Quarkus. It's in the files page, and it can be also visited from the tutorials page. As an exploratory analysis, you can do a quantile plot or QQ plot against a normal distribution. So this QQ plot plots the quantile of your distribution against a quantile of the normal distribution. So if you see that the QQ plot follows a 45-degree straight line, then you are fairly certain that the distribution follows a normal distribution. So is there any questions about the normality assumption? So normality assumption is one of the things that are usually ignored by the researchers, which are very, very big mistakes. They don't really carefully check whether the data distributions follow the normality distribution before running the test. These are actually huge mistakes. We need to first check the data and understand that this data actually follows the normality distribution or the Gaussian distribution before running the t-test. Otherwise, we should use the Mann-Whitney-U test instead. So to interpret the test result, the p-value approximately means how likely is the sample mean equal 100. So if p-value is very small, like smaller than the significance threshold, we can reject the null hypothesis and state that we find something new. Otherwise, we do not have sufficient evidence to reject the null hypothesis. So this sentence is going to appear frequently. When you read the papers and if you see some report about some scientific findings, usually you can see this sentence. You do not have sufficient evidence to reject the null. This is just a more fancy way to say that there's no new finding here. And there is also a term, degree of freedom. In the one sample t-test, the degree of freedom equals n minus 1, where n is the number of samples you have. And why is there a degree of freedom? So like I said, the t-test gets its name from the t-distribution. And t-distribution is the distribution of the mean of the samples from a normal distribution. And this t-distribution is parameterized by the degree of freedom. So the more samples you have, essentially the more degree of freedom there is. So for example, if you see that from one sample, the average tweet length of this one sample is like 101 or 200. It doesn't really mean anything because it is just one random sample, and it can be, for example, if the tweet length is equals 141, it might be some bug of the Twitter system. But if you see that out of 1,000 or 2,000 samples, the average tweet length is around 100, let's say 100.1. then then even if the observed mean is very close to the hypothetical mean, the strength of the finding is different from the strength of the findings in just one sample. So the t-value essentially measures the scaled mean. So my point is that with the same t-value, that results in different p-values. So let's make another comparison. So in an exam, you get the raw score as t and the percentage score, that percentage in the class as p-value. So if you get, for example, the top 10% as p-value in a class with size only 10, then it probably means that you're ranking the first one in this small class of size 10. But if you see if you are in the top 10% in a very large class size, like in the class size of 200, then this means something different from the previous finding. So although you have the same raw score and there's the same p-values, you should also take the degree of freedom into consideration. And actually, when reporting the results, usually people report the p-value and the degree of freedom. And if the p-value is smaller than 0.05, they just say that here's our finding, and we reject the null hypothesis because the p-value is very small. And as a side note, the degree of freedom is for example, 99 or 49 if you have n equals 50. So the degree of freedom describes approximately the strength of your finding. Question? N is the number of samples you have. It's the size of the sample. So here, n equals 50 in this example. So n is the size of the array you pass into the t-test one sample function. So like you mentioned just now, the alternative hypothesis can differ. So usually by convention, the alternative hypothesis refers to that the length of the tweet is different from 100. This corresponds to the two-sided t-test. So the true mean of the population can go in both sides of the hypothetical mean. So it could be larger than 100 or it could be smaller than 100. And either one could make a meaningful alternative discovery. So this is the default setting in the t-test one sample function. There's also the alternative to set to greater, which gives you one-sided t-test. So in one-sided t-test, the alternative hypothesis is that the population mean is greater than 100. And there's also the flip side. The population mean is less than 100. So if you want to test whether the mean of his length is different from 100, then use a two-sided t-test. If otherwise you want to test whether this length is greater than 100, then use a one-sided t-test with the alternative set to greater. So which test to use really depends on what you want to test. And actually, the type of the t-test, the selection of the type of t-test should be done before you run the t-test. And after you see some test results, do not change the type of t-test. So usually some people see that the p-value equals like 0.06 or 0.07, and they are kind of disappointed that this result is not significant. And they found that they originally set up the test to be one-sided. And then they changed some people might change the type of the testing to be two-sided, hoping that they will see some more significant p-values. And usually they succeed. But this is incorrect. This is called p-hacking. And p-hacking essentially gives you the false scientific discovery. With the p-hacking, you discover something that is not there, is not true. And essentially you report some spurious findings. I will talk more about p-hacking in a few slides. But for now, let's just say that before running the t-test, select a suitable type of test before you run the test. And then after you get the result, just record the result and just report it, whether or not it's significant. Great. Let's take a look at two-sample t-test. So two-sample t-test can handle this type of questions. I add a layer or make some changes to the hyperparameters of a system. And is the prediction accuracy better than the baseline? So the alternative hypothesis is that, yes, the new configuration has a higher accuracy. The new layer to the neural network is useful, is meaningful. We should add more layer to the neural network in the future experiment. And the alternative hypothesis, and the null hypothesis is that otherwise, the prediction accuracy does not change. So usually when observing the prediction accuracies, we observe the accuracies of several random seeds. So you run the same neural network with different random seeds several times, usually 5 times with random seeds, or for example, 0, 1, 2, 3, 4. And then you collect 5 numbers at the accuracies. So after changing the hyperparameters, you get 5 accuracy numbers. And before changing, you also get 5 accuracy numbers. You want to compare whether the accuracies after changing the hyperparameter is better than the accuracies before. So you are sampling from 2 random variables at the same time. So you need to do a two-sample t-test. And in the scenario I described just now, N1 and N2 both equal 5. So N1 can be different from N2. But usually for convenience, I'll just say that you take 5 from the experiment before changing the hyperparameters and 5 from the experiment after you changing the hyperparameters. And then the procedure for doing two-sample t-test is that you plug into the equation, you plug into the function t-test IND. IND means independent two-sample t-test. So you plug in the array consisting of the old result as well as the array consisting of the new result. And you also get a t-value and p-value as the testing results. So here are some notes. The population means of both random variables are unknown. So you only know the observations or the samples. So the experiment results, the 5 accuracy numbers from the experiment results are the samples. They are samples from the population, but the population itself is unknown. The population itself is a random variable, and it has some intrinsic randomness. And the 2 populations should be independent. And if the 2 populations are dependent, you should use the parity test, which I will describe in like 5 minutes. So in order to make sure that these 2 populations are independent, I sort of collect different experiment results by varying the random seeds in both of the experiments. And usually by taking the random seeds 0, 1, 2, 3, 5 in both experiments, the two populations, the samples from the two populations are independent. Question?
About this independence assumption. So does it also require that, for example, we run these neural networks on different data subsets of something? Like how far should we go in ensuring the population independence?
Yeah, that's a good question. So how far should we go in ensuring the independence? Usually varying the random seed is enough. You run on the same data set, you use the same optimizer, and you just take different random seeds. And all the hyperparameters, like the choice of optimizer, the neural network architecture, are set to the same, except for the hyperparameter that you want to change. Yeah. Question?
Could you not argue that because the second neural network is just the first one with an extra layer, that there is some dependence there, that the architectures are related, and so there's going to be some dependence?
So the point of
Just the random seed mostly utilize that.
So this is the independence is in the independence of the sampling from the population. So you can say that these two populations themselves are related by the same neural network architectures, but the sampling procedures are independent. And the sampling procedures independence is ensured by the random seeds you take. And the point of this test is to control for some factors that you do not care about, and only vary in one factor. And the factor that you want to vary is the additional layer of this neural network. So the difference of this testing result is going to be actually the difference or the effect of adding this layer. So you are controlling for other factor, but just varying this factor so that the result is going to be the treatment effect. And like always, the p-value approximately means how likely the two population means are equal. And if the p-value is too small, we reject the null hypothesis. Question?
Can I ask if there are any conditions like the two populations have a different size, then yeah, it's very different, or the sample size are very different?
The size of the population is unknown. Populations are random variables, and you can only draw from the samples. And you can definitely draw the same sizes of samples. So in that case, N1 equals N2. Okay. Question?
Do we not need to assume that the two populations are normal here?
Two populations are normal. Yes, both populations should be normal. Yes. Any other question about the two-sample t-test? Okay, great. Let's take a look at the parity test. So this is the case where the weight of the participant is dependent on both the recipe and the participant itself. So there are actually a lot of intrinsic variance within the weight of the participant. So some people could try a very useful recipe, but in the end the weight is still larger than the other participant who does not try this very useful recipe. So if you sample from the participant before trying this recipe and those participants after trying those recipe, then the randomness within the participant is going to outweigh the effect of this recipe. So in order to remove the effect of the differences between the individual participants, we need to run a parity test. So the procedure of running the parity test is that we first hypothesize that for example, if the recipe changes the weight or not. Actually, there are some typo here. This should be H1 and H0. The null hypothesis is that the recipe does not change the weight, and the alternative is that the recipe changes the weight. And we collect all the participants' weights before and after the trying this recipe for a month and plug in the t-test REL function. So in this function, we require the length of two arrays to be the same. So and actually their sequence should be exactly should match exactly. Yeah, question?
In the neural net example, wouldn't it be like far more meaningful to use paired t-test instead of two-sample t-test? Because basically with paired t-test, I can assume like I have, I don't know, 1,000 data points, and I train a neural network on them without a layer, with a layer, and basically feed in like per sample accuracies, or per sample like binary labels, like correct prediction and false prediction. So basically, I automatically have very large sample sizes, the amount of original samples in the testing data set, instead of like 5 or however much different neural network runs that I can afford.
So the in the neural network example, the randomness introduced by taking the random seed is not relevant, and it's not something that is relevant to the effect of adding a new layer. So there are the effect of random seed, and there's the effect of adding a new layer. So there's no, so these two effects are actually already quite independent. So you can take the two-sample t-test. So let's frame it this way. So when a neural network structure or hyperparameters is decided, no matter how you set up the random seed, does not in principle change the performance. It does not change the true performance of this neural network. So varying the random seed only affects how you draw from the population, but there's no causal relations between the populations before and after you change this hyperparameter configuration. But in the participants trying recipes example, the individual difference between the participants actually are closely related to the effect of the recipe. So some people might be less responsive to the recipe, and some might respond some might be affected by the recipe by a lot. So you really need to control for the individual differences by applying a paired t-test. Okay. Question?
So can I summarize that the difference between two-sample t-test and paired t-test is the population may not be independent in paired t-test?
Yes. Actually, in paired t-test, the two groups of samples it's more than dependent. There is a one-to-one correspondence in the two pairs of samples. So the randomness in the paired t-test only comes from the how you sample from the population of the participants, and they are the same population. So here in the paired t-test, there's only one population to sample from. So it makes sense to frame the paired t-test as a one sample t-test from the difference. So actually, I'll describe that in two slides. So the degree of freedom is n-1. A paired t-test is equivalent to one sample t-test of the differences against 0. And like always, if the p-value is smaller than 0.05, then reject the null hypothesis and conclude that the alternative hypothesis is the finding. So here, if we incorrectly use two-sample t-tests when there are obvious one-to-one correspondence between the two groups, then the p-values could be inflated. So the p-values inflated, meaning that you might conclude that there's the recipe has no effect when the recipe actually has some effects. So as a summary, there are three types of t-tests to consider: one sample, two sample, and paired t-test. So one sample t-test worries about whether the population mean equals a hypothetical population mean, mu. And two sample consider whether the mean of two populations are equal to each other. And paired t-test consider whether the difference between the two populations, between the two random variables, equals a known value. Usually, the known value equals 0 when we set up the paired t-test. And the function to run all of the three types of t-tests can be found in SciPy. And also, if you use R, there are some corresponding convenient functions in R as well. So there's 5 minutes left. Let's quickly go through the multiple comparisons. The point of multiple comparison is that if you are running a lot of comparisons, a lot of t-tests at the same time, there are some probability that some of the findings will occur as significant by accident. So although those observations are, although none of the statistical tests are not significant, they can still appear significant. Some of them could still appear significant, and that is just because of the randomness. So this, I don't think we have time to go through this computation example, but the point is that if you flip a lot of coins, and if you flip like 100, 200, or even 1,000 coins, some of them will actually appear biased by accident. And the more coin you flip, the less likely is that when you don't observe any of them to be biased. So, for example, if you flip 173 coins, it's almost certain that some of these coins will appear biased by accident, but none of these coins are actually biased. So in order to correct for this multiple comparison effect, the way usually people correct for this effect is Bonferroni correction, which is just divide the significance level by the number of comparisons you are doing. So for example, if you're doing 173 comparisons, divide the significance level by 173. And the p-value will need to be smaller than this new threshold in order to be considered significant. So this is a very, very large correction. And usually after Bonferroni correction, almost all of the significance tests will be insignificant, because the p-values are going to be smaller. The p-values are going to be larger than this very small new threshold. There are a lot of other types of corrections as well, in order to correct for the multiple comparisons, and you can check out Wikipedia if you are interested. Question?
So, like in a joking example, assuming I know that an author of a certain paper, for example, performed p-value hacking in order to get significant results, but I know that they tried 10 different configurations of tests of their parameters until they arrived at the p-value that they like. So I can use Bonferroni correction on what the results they obtained to get a new value of significance that they would need to beat for their results to still be significant.
This is kind of relevant to the p-hacking. This sounds like you are describing a scenario of p-hacking. Like before before doing the t-test, you should select and decide the type of test and type of correction that you want to apply. And Bonferroni correction essentially changes the significance level. So it should also be configured before you run the t-test. And after you see the results, just report the result. Yeah. So p-hacking is I kind of mentioned that before. Once you get the results, do not do any of the following to try to, for example, increase the significance. That includes, but is not limited to resampling the data or change the type of test, like change from one-tailed to two-tailed, or change the type of test and pick a significant one and do a lot of different hyperparameters and select a significant one. But actually, I think it's meaningful to do a lot of, to try a lot of different hyperparameters and select the best one, but not for the purpose of making the p-value significant, but for the purpose of finding the best hyperparameter or finding the best architecture. So these are different things. Finding the best architecture and finding the significant p-values are different things. And the harm of p-hacking is essentially a discovery of some new knowledge, the discovery of some false knowledge. And in writing the paper, if the statistical test does not have p-value smaller than 0.05, I'll just say that the result is not significant and also report the p-value in your report. So that essentially concludes this lecture. We briefly look at the statistical test, t-test, and a multiple comparison problem. And starting from the next few lecture, Raid is going to describe the neural language model and hidden Markov model. And after that, I will come back to describe natural language understanding and speech recognition, etc. Yeah, see you.